let's discuss definite integrals and do some examples. So as we know by now, a definite integral gives us the area under a curve, and the curve that is defined is the integrand. So the function inside the integral is the curve. So let's start with a pretty concrete example. Let's say we want to take the definite integral from 0 to 1 of x squared dx. So before we do anything here, let's think about what this means. So first thing I'm going to do is I'm going to graph x squared. So we have our y-axis here, and we have our x-axis. And we all should know that x squared is a parabola that looks something, let's make that look nicer, something, oops, okay, it seems like I can't make it look nice. Alright, that's good enough. Something like that. And then we also have, actually hold on, that's bothering me. Let me use this. There we go. And we only care about from 0 to 1, so I'm not going to write the left side of the parabola. So let's just say this is the origin, so it's pretty clear, and this right here we'll say is x equals 1. So us taking the definite integral from 0 to 1, what we're doing is we're giving a bound to this curve at 1, and also the x-axis is always the bound. And what we're doing with this integral is we're taking the area under this curve. And this is useful in a lot of applications of physics, engineering, and other things. And also, if you want to take the area of this, this shape, you can't really do it with any other way. You can't use geometry because this is not a triangle or a circle or any of that common shapes which we have formulas for. So we have to use an integral to take the area. I mean, you could estimate the area with a triangle, and if you haven't seen the videos on those, which are called Riemann sums, then you should watch those. But we can sort of draw a triangle like this, and we can say that this area is probably around the same area of this green triangle that we just drew. But that's just an estimation. So if we want to be accurate, we take the we take the integral, and we find the area under this parabola, which is x squared. All right, now let's do it. So what we want to do to take this definite integral is we want to think of it as an antiderivative. So I want to think of a function whose derivative is this right here. Another way to think of it is you could think of it as just an anti-power rule. Instead of subtracting 1 and multiplying by the power, we add 1 and divide by the power. So in this case, it would be x to the 2 plus 1, which is, actually let me do a different color. So it would be x to the 2 plus 1, which is 3, and then divided by the power, divided by 3. And for definite integrals, we don't do plus c. And actually, there's a reason for that, and I'll show you the reason. So we technically do plus c, but let me show you why the c doesn't matter. So it's x to the third over 3 plus c from 0 to 1. And this little bracket thing is just, we want to remind ourselves that it's from 0 to 1. It doesn't really, you don't have to write it like that. You can write a line or whatever you'd like. Anyway, so now what we do is we evaluate this function at 1, and then we subtract that evaluation at 0. So let's do that. So we plug in 1. We get 1 over 3. Sorry, 1 to the third over 3 plus c minus 0 to the third over 3 plus c. Alright, so let's see. 1 to the third is 1, so we get 1 over 3 plus c, minus 0 to the third is 0, so minus 0 minus c. And notice that the c's just cancel, and that's actually the reason why we don't care about that constant when we take definite integrals. So next time you don't really have to write the c. And again, technically the c is there, but we just don't care about it with definite integrals because they cancel. So we get 1/3 minus 0, which is just 1/3. So the area under this parabola from 0 to 1 is 1/3.